Lesson 1.4 in curve sketching is going to be important for you to understand how it is that we know that a graph looks the way it looks and trying to put everything together into one place. This is not actually on the AP exam. It's a conceptual piece. It helps you understand what it is that you're doing when you move forward into the rest of this year. So we've already talked about domains, vertical asymptotes, holes, x-intercepts, y-intercepts, and end behaviors, as well as whether or not a function has even or odd ness around the origin or around the x-axis. And so we're just reviewing. When you get lost, come in here and look. Oh, I don't remember how to find x-intercepts. Well, there it is. I don't remember how to find end behavior. Well, there it is. Okay, so feel free to just refer to this part of the section anytime you need it. So for examples 1 through 3, it says give the domain, reduce the function, find vertical asymptotes, holes, and end behaviors. We look at x plus 2 on top and x squared minus 2, x on bottom, and we know we can factor this, and that's fine because it helps us figure out a little bit about the domain, right? So I'm going to factor this into x times x minus 2, and that means that I can say that x should not be 0 or 2. That is not in the domain. So I'm going to put a does not equal symbol, and there you go. And then when I want to look at this problem a little bit further, I say, does that mean that there is vertical asymptotes there at 0 and 2? And in my mind, I'm thinking yes, because that's an odd exponent and that's an odd exponent. And we know that they aren't removable holes. So we know the behavior here has got to be some sort of infinity or negative infinity. And we're going to sketch that in a later problem. So we'll decide when we get there. But in the meantime, I say yes, that there is a vertical asymptote, and that happens when x equals 0, and it happens again when x equals 2. Now, as far as end behavior, here's where we're talking about it, right? We are going to take a look at these first two terms because they are the highest degree in our expression, and we're going to say, yeah, that shady math, something is approximately equal to x over x squared. That can be simplified into 1 over x squared. And you're supposed to be feeling really comfortable with the shape of that graph by now and know that it has end behavior that goes towards 0. So remember what the shape of that graph is. And hopefully you would be able to sketch it just any time. And right here is my horizontal asymptote that says that it is approaching a value of 0. And so I wanted to mention that when we were doing end behavior, we it came up naturally in our discussions around the practice that a horizontal asymptote is the same thing as a limit at infinity. So here we go then. We say that when x is going to positive or negative infinity, then y will be going to 0, which is the same thing as the x-axis. And that is something we can write down as a value. Horizontal asymptote is going to be y equals 0. Remember that the x-axis and has an equation, and its equation is y equals 0. So for the next one, we again look at the denominator, and we're going to say, hey, the problematic value for us is when x equals 3. So let's restrict that. Let's say that x cannot equal 3. And then our vertical asymptote, is even. It's even. So that'll be important to us when we want to calculate the end behavior. And we're going to say that we know that that vertical asymptote is happening when x equals 3. And then we want to say, well, let's take a look at the first value, right? The terms that have the largest degree. And so I'm saying I have my shady math right here, which is that this function is really close to 2x cubed over x being, ready, squared. And then I can simplify that then into y equals 2x. And that's going to be a graph that I can recognize, right? The graph of y equals x, I know what it looks like. Y equals 2x, it looks basically the same, but the slope is a little bit steeper. So it'll go like this in one direction, and it'll go like that in another direction. And we're actually going to graph that in a little while. But just to mention, that means I could part together an actual limit here. And, and the limits would be different for each side. So the limit as x approaches positive infinity of g of x is going to be positive infinity, and that the limit of g of x as x approaches negative infinity, sorry about that infinity over there, let me fix it, is going to be negative infinity. But we want to actually sketch that. So we're going to try in a problem here in just a minute. We're just practicing the basics right now. So taking a look at number 3, h of x is clearly factorable. And that means there might be something that can cancel out. So let's factor that. Two numbers that when you multiply them, you get -8. But when you add them together, you get 2. I'm thinking are 4 and -2. So x plus 4 and x minus 2. And you can factor that in some boxes if you're not feeling like you see it right away. Just take a moment and factor it, and you'll see. And then this is going to be x plus 2 and x minus 2. And boom, those disappear. And so my function will end up being, oh, look, I wasn't even looking. Yeah, here, he already factored it for you. Okay, so the x minus 2's cancel out, but that doesn't mean that it's not in the domain, right? In the domain, I still have a problem at 2. I also have a problem at -2, but one of them is removable. Okay, great. So we'll have to remember to put a hole, down sometimes when we graph. So let's say then the domain is such that x cannot equal positive or -2. And then what does my function look like when it's reduced? That's what this means, by the way. He's like, hey, what does your function look like when it's reduced? Okay, well, let's say then that it looks like x plus 4 over x plus 2. And if I'm trying to figure out, the rest of this, where the vertical asymptote is, I know that it's not where I removed a hole. So the hole is at x equals 2, which means the remaining number, -2, that's where my vertical asymptote is. So x equals -2. And then also I want to mention that looking at this function, there is a hidden invisible 1 right there. And so that means that it has odd behavior. And so I'm expecting n behavior. Oh, wait, he says right here, here's a place to put the hole. Again, things I didn't notice before. X equals 2 is where the hole is at. The end behavior then, I want to say, because it's odd, I know that it's going to go up in one direction and negative in the other direction, and I just have to figure out what that looks like, right? So I'm going to, do my shady math, and I'm going to say that something, just something in general, looks like this. Ready? X over x, which is equal to 1. So I'm guessing then that I'm going to have end behavior that approaches a particular number, and that means that's a horizontal asymptote. So my horizontal asymptote is going to be at y equals 1. Okay? And so now we have the basics of how to do it. Let's get into some actual sketching. And we're going to try and, follow this recipe where we give the domain, we reduce f of x, and we're going to factor in order to do that. We're going to find these vertical asymptotes and where the holes are. We're going to look for x and y intercepts, and we're going to find the end behavior. We're going to, double check where those horizontal asymptotes are, and check for symmetry. Maybe if you need to, find a starting point, and then we're graphing. But actually, I would say that it's a good idea for us to, graph each piece, if we can, as we do it. All right. So when you find a vertical asymptote, mark it. And if you find the x and y intercepts, mark them. And then end behavior, let's give a little quick sketch of what that looks like because we know that's, off to the sides of the graph. And then we're going to try and see if we can't put the whole thing together at the end. So we have this curve and we want to sketch it and we're looking at it and it's not rational. So that's great. So I'm going to say that my domain is all real numbers, right? All real numbers. And you actually don't even have to do all. You can just do that symbol and that means all real numbers. And I'm thinking about when I look for an x-intercept, I'm trying to say when y equals 0. So if y equals 0, then I could say that I have the ability to set each piece equal to 0. So I've got x equals 0, and I've got x minus 1 equals 0. So I could solve for that and get x equals negative 1. I'm sorry, positive 1. And then I can set x plus 2 equal to 0, and I'm going to get that x equals negative 2. And those are going to be my x-intercepts. And so I'm going to graph them really quick, right? So here's a 0 right there, there's a 0 right there, and there's a 0 right there. So this graph is going to go through all three of those points. Now, on the y-intercept then, let's see what we think it would be. That's when I set x equal to 0, right? So I'm going to set x equal to 0. So I just want to kind of plug that in real quick because it's easy to make a mistake if you go too fast here. So y equals, ready, 0 times 0 minus 1 times 0 plus 2 squared. And right there when I plugged in the first 0, I realized that y just equals 0. So my y-intercept is just y equals 0. So I actually do write stuff down, otherwise I get confused. So I recommend that for you as well. And I've already graphed that point. It's right there in the middle. So what is my end behavior of this then? I will mention that altogether, what kind of polynomial would I end up having? So I have an x here and I'm another. So my shady math, remember, says that this is approximately equal to, and I'm not going to expand this whole thing because I really don't need to. I just need to know what the degree of the highest term is. So I have x times, ready, another x times, ready, another x and another x because there's two of factors there. So an x times an x is going to give me an x to the fourth. And I remember that end behavior then would be like this. Ready? Going to positive infinity and going to positive infinity. So how can I get all of these points to kind of come together? Well, I know that, graphs like this, polynomial expressions that are not rational, they are, remember the basic one, right? X cubed goes like this and goes like that. But then we have seen examples where x cubed could go high and then low and then high again. And so I'm assuming that this x to the fourth function does the same thing, but it just ends high and it ends high. So how can I connect these things together? Well, ready? I'm going to go like this, and I'm going to say that I know that it bounces off. And here's why. Whenever you have a number that, a factor that is got to come back around to another point, um, and here, let me try the other side. So from the other side, I know that I'm going to positive infinity, but I can't cross over the x-axis, right? Or, okay, so how do I graph this? So I know that I have this and I have this, right? And I'm trying to remember how to know when it bounces off. Oh, right. Okay, so now let's try to actually graph this thing. with, this the idea that we know that it's like an x cubed, but it's x to the fourth, and it's going to bounce down, it's going to go up, and it's going to go down. When do we know whether or not something actually crosses the x-axis? Because I have a lot of, directions that I could be going in the middle, and what I'm hoping you recall is that if I'm going to come in here and erase this, if you have a degree that is odd, then it goes through. It actually crosses the x-axis. It doesn't bounce off of it. If it's odd, it doesn't bounce off of it. It actually goes through. And if it's even, if it's even, that's when it bounces off the x-axis. So if you don't remember that from pre-calculus, don't worry about it. It's possible that you never did much curve sketching there. We know why. We know why we didn't get a chance to do it. So here, I'm going to say that bounces off. And then it's going to go to some kind of high. And, where that high is, it could be up here, I don't know. It could be down here. It could be right here. That's calculus. That's the part that I'm dying to get to teaching you. So exactly where that local maximum lives, I can't say. So I'm just going to pick a value and I'm going to go for it. But you can actually plug in, that you think. And what do you think? Do you think that it's got to be exactly halfway through? So what is going on here at -1? You can actually plug that in to your calculator and find out that that height is a 2. But I want to teach you the tool for being able to find it, in the next chapter. Okay? So here we go then. I say then I have to go back down to 0. And here with these two, again, I know that they actually go through the x-axis, and then they're going to go to some sort of low. And I'm imagining that that low is probably at a half. And if you plug in a half, you will actually get this point, and then boom, you can find that. So now that you've seen me do an actual curve, how are you going to reproduce your graph? Well, I mean, I won't lie. I expect a lot of you are going to graph them on your calculators and you're just going to try to copy it down. So, that's fair. I'm allowing that. I can't stop you from doing that. But you want to at least try to do all these middle pieces by yourself, okay? And I need you to know that there's another curve sketching section later on in the book, once I have taught you how to locate this number without guessing, and how to locate this number without guessing. Where exactly that local max is, where exactly that local min is, that's something we'll be able to find. We won't need to guess. We won't need to eyeball a graph. We won't need any help. Okay, we'll have a tool, an algebraic tool, to be able to find it. All right. And by the way, I love this section. It's very dear to my heart because I did not have a calculator. I did not have a graphing calculator when I was in high school or in college. So this is exactly how I learned to do it. Those sorts of tools, definitely the TI-84 was out when I was in high school, but I didn't know anything about it. I don't ever remember any of the students in my class having them either. I just don't think they were very I don't think they were very well known. My teacher definitely didn't use one. Never displayed anything like that on the screen. So this is the way that we used to do it back in the day. Okay, so for number 5 then, I did want to mention one little thing, which is that this right there, read, R-E-D, it means reduced. Okay, so it's not obvious if you've never seen calculus teachers like to use a lot of subscripts. So that means reduced, and that means that this up here, it can actually be reduced. I'm sure of it. Think about it. I have an x over an x squared. Those simplify out into just regular x. I have an x minus 1 squared on top with an x minus 1 on bottom, so I can reduce that. And then I have an x plus 3 and an x minus 3. Those guys aren't the same, so they can't be reduced. So then my reduced function, I would say I have an x minus 1 on top, and I have an x plus 3 quantity cubed on top. And on bottom, I have an x, and I have an x minus 3, and that is still squared. Okay? But don't forget that just because you reduced it doesn't mean that stuff isn't still restricted in the domain. So in my domain, I still say that x cannot equal 0. And that's because I have x in the denominator. And so it can't equal 0, or else I'll have division by 0. I also am finding that even though I got rid of the x minus 1 on top, if you set that equal to 0, you'll find, hey, I'm still not allowed to be equal to 1, because even when you reduce it, it's still a whole there. And then I have another domain restriction at 3. So when I'm thinking about those, I'm not exactly sure if I have an asymptote or a whole, right? Until I'm sort of looking at it. What does that mean? So when I'm looking at it, then the 1 was removable. It was completely removable. And so I'm going to call that a whole, and I'm going to mark that whole down. And then 0 was not removable. I reduced part of it, but part of it still remains. So that ends up being an asymptote, okay? And then at 3, boy, I didn't remove any of that. That is also definitely going to be an asymptote. And I'm just going to mark those things down right now, as they'll help me as I move forward. And so I'm going to mark that whole as saying that it's 1, 0. And by the way, when I reduced it, it was a single factor, right? So there was a hidden invisible exponent of a 1 right there in the denominator. That means it's odd. So it will go through 1. And it's either going to go through 1 like this, or it's going to go through 1 like that. And I'm not exactly sure yet, but it is going to go through. So I just wanted to mention that. And then I have also vertical asymptotes that I can write down where x equals 0. And that is also odd because I did reduce and got down to just regular x to the first power. And so that means that that's odd, and it's going to go through. But it's a vertical asymptote. So oddness in this case, sorry, let me remind myself. Oddness means it'll either go like up like this and down like that, or vice versa. And so I just need to figure out what direction those things go when I'm working on this, okay? So then another asymptote that I have at x equals 3, that one, right, when I set this factor equal to 0, then that'll be at 3. And that one is even. So at 3, I know that it'll either go up like this in both directions, or it'll go down like that in both directions. And so now I want to try and figure all those little pieces out. And when I actually draw my graph, I thought it might be fun to use a different color. Oh, it's October. So I want to be using, I guess I'm going to use orange. So I've got all of those pieces that I've marked, and I'd like to try and decide whether or not, for example, let's look at 3, okay? So if I look at 3, what kind of numbers am I getting out of each piece of my function? And I'm going to take a look at the reduced function, because I just think it's a little bit easier to work in this space. So if I plug in a 3 minus 1, I'm going to get a positive number. I don't care that it's 2. I just care that it's positive. If I plug in up here a 3 plus a 3, again, that's a positive number. And all positive numbers being multiplied together will also give me a positive number. What about in the denominator? If I plug in a 3 here, I get a positive number. Down here, I'm worried, right? Remember, I know that I have my asymptote. So imagine then, what if I plug in a number that's just close to 3? So I could pick a number that's bigger or less than 3, because remember, I'm expecting that both sides will have the same behavior, either up here or down here. So I don't care which direction I'm coming from. And so I'm thinking, well, why don't I just check what happens when 3.1? I plug in 3.1. In fact, all of those numbers could have been 3.1s, and I still would end up with positives. Okay? It doesn't matter if I pick 3.1 or if I pick 2.9, because down there in the bottom, I'm squaring it. 2.9, it would have ended up with a negative number, but then when you take a negative times a negative, you end up with positive. So I get positive behavior on top and on bottom when I'm plugging these numbers in. And that means that I know, ready, that it goes up like this. The other thing I'll say is that I know something now about the other side. Yeah, that other side is being forced to go through because I knew that my hole was at 1 and I knew that it was an odd hole, meaning that it goes actually through. So that root is odd, means it goes through. And if it's going to go through, then it has to go down to a negative infinity on the other side. Now, this part also will have that kind of behavior on the other side. But I'm not exactly sure. I haven't talked about end behavior yet. So I've just talked about behavior around my asymptote, and I'm feeling really proud of myself because I got a bonus out of that, right? I got the bonus of figuring out what's going on at 0. And because I know what's going on at 0, remember that 0 was an um, odd vertical asymptote. That means if this part's going down, then this part has to be going up. Okay, so that was all fascinating stuff, and let's see what else we might be able to find. For example, I'm curious about an x-intercept. Okay, how could I make all of this be equal to 0? How could I make all of this be equal to 0? Question mark. Is there a way for me to do that? Well, yeah, I could definitely make there be a 0. And here's one thing I could do. I could plug in a negative 3. And if I plugged in a negative 3 on the top, then I would negative 3 plus 3, that's 0. So I definitely have, ready, an x-intercept right here. Now what about the other intercept? Well, up here on top, if I did 1 minus 1, I do end up with a 0. But remember, 1 isn't in my domain. Okay, so when you are looking for x-intercepts, I'm hoping that you remember that you're trying to figure out when you can create a situation that that you get a 0 for the entire function. So you set the whole thing equal to 0. But why am I not looking at the denominator? Because there's this little trick that I recall, okay? So say, for example, I had like, say, a 2x over, say, a 5x, minus 7. And that's not something that you can reduce. When you set that equal to 0, ready? I like to clear my fractions. I like to get rid of them. And I literally mean get rid of them. Over here, I'm going to multiply both sides by 5x minus 7, and I get just a 2x. Over here, all of that was just 0. So when I just set the numerator equal to 0, that's a trick that I remember, is that when you multiply both sides by the denominator, if you're multiplying the denominator times 0, you just get 0. So whenever somebody just sets the numerator equal to 0, that's why they're doing it, okay? So now I know that my x-intercept is at negative 3, and that's when I get a 0 for y. And so now I want to say that I'm interested in figuring out what the end behavior is, because while I'm pretty sure it's pretty easy for me to figure out how to curve these together, I don't know if it's going to bounce off or if it's going to go down. And so let's take a look then at end behavior and y-intercepts, okay? So y-intercepts, like if I had this, if I had y equals, mx plus b, y-intercept is easy to find. Even in a quadratic equation, if I said like y equals, x squared minus 3, hey, you would know that the y-intercept is negative 3. There's no number by itself that's being added or subtracted at the end. So for a y-intercept, I'm guessing that 0 is what I would like to say. But remember, it's asymptotic at 0. So there isn't any y-intercept, none, okay? And the reason why is that we cannot use x equals 0. It's not in the domain, okay? So now that we've checked that, let's do end behavior. And end behavior, we want to take a look at what kind of equation we've got going on here. And so my shady math says that I have, and by the way, it doesn't matter if you use the original or if you use the reduced, okay? So I'm going to use the original, and then if you want, if I have time here, I'll use the reduced. And there's some spare writing on my screen. I got rid of it there. Okay, so approximately equal to, ready? I have an x, and I have 2 more x's, because ready, this is squared. So that's x squared. And right here, I have 3 more x's. So that's going to be x cubed. And all the way across the top now, I have x to the 6th. Down here, I have an x squared. And right here, I have an x. And right here, I have another set of x squareds. And that is going to be x to the fifth, which means that when I reduce that, I end up with just an x. And remember, that's a straight line. You remember that line, I hope. Remember, it goes like this, y equals x. So that's my end behavior. Okay, that's going to be my end behavior. This line has got to curve back around and go up to infinity that way. And it has to keep going through here and go down to infinity in that direction. Okay, so ta-da, we just made a very complicated looking graph, and I'm so proud of us. If you felt like this was hard, then I don't blame you. You really have to do calculus for a long time to be able to do these kinds of graphs. All right, it's definitely no joke. When I look at number 6, I'm noticing that we have this situation again that we've talked about in class. We've done a couple of practice problems where I'm wanting to do my shady math like immediately. You know, I see that this is basically equal to x over ready, the absolute value of x. And so I already feel like I know the end behavior, and I'm hoping that you're with me, that we've gone over stuff, questions in class, that remember, if I am going to positive infinity, then this number would be positive and that number would be positive because I'm just plugging in a bunch of positives. So I know that this reduces, ready, to just a positive 1 as I'm going to infinity. So right here, I'm going to mark that 1, and I'm saying at some point here, I definitely know that I'm going to 1. How about in negative infinity? Okay, so when I'm going to negative infinity, what do I notice? I see that I'm going to plug in a negative on top, and I'm going to plug in a positive. I mean, I'm plugging in a negative on bottom, but then I'm taking the absolute value of it, so it's going to be positive. So I know that down here that I'm going to end up with, ready, a negative 1 as my end behavior. So somewhere in this direction, I want this to line up with this negative 1. I'm going there. So I now know what my end behavior is. And I will use just a little bit of, I don't know, some notation here so that my shady math, makes some of you uncomfortable. Let's say that we're coming in from the right and meaning, or we're going out from the right. We're going to infinity. And we say that we have this y equals x over the absolute value of x. And then will mention that this is where I want to write that positive 1 over the absolute value of positive 1. And that's how I get 1. And then let's down here say that we have, that is our horizontal asymptote. Okay. And here I say that I have another horizontal asymptote on the left. And I'm talking about as x approaches negative infinity, and that this is the same function, that shady math is approximately equal to, ready, approximately equal to, it's going to be equal to negative 1 over the absolute value of negative 1 gives me a negative 1. Okay, so that's me just writing a little bit down about that. So what numbers are not allowed to be in my domain? Definitely x cannot equal 0. Okay, absolutely not allowed there because I would end up with a division by 0, and that's bad. And so I'm going to say that that has got to be my vertical asymptote, is that x equals 0. And as far as holes go, there's nothing really that I can simplify, so I'm going to say none here. What about an x-intercept? Well, I notice that in order to get the top equal to 0, I said x plus 1 equal to 0. I'm going to end up with an x-intercept at, ready, at negative 1, 0, because I solved. And by the way, that's odd. So I know that I have an x-intercept. It's right here, and it has to go all the way through, okay? And as far as a y-intercept goes, again, I want to say that there's a hidden invisible plus 0 right there, but we're not allowed to use that because it's not in the domain. So there's no intercept, y-intercept, because we have an asymptote there. So that means we kind of have to sort of like pick what we're going to do here. And by the way, I will mention, I forgot to say something about this horizontal asymptote. That horizontal asymptote, it's even, okay? It's definitely, vertical asymptote, it's an even asymptote, meaning that it's going to either go positive or it's going to go negative. And so when I try to think about those numbers, remember that you're squaring everything in the bottom, so you're always going to end up with a positive. And as you get close to zero right here, you're plugging in a positive number, you're going to end up with a positive. Okay? So I'm going to say then that this is positive and this is positive. And I'm guessing, remember that I had that horizontal asymptote at 1. So I'm guessing this is what this looks like. Okay? And you're going to confirm on Desmos anyway. On the other side, I said I know for sure that it goes down, and I also know, ready, that it goes towards -1 as a horizontal asymptote, as my limit as we go to negative infinity. So there you go. There's your graph of that.